Hi and welcome to the lesson about signed operation. We are still learning about basic assembly. Objectives of the lesson. We will learn about the neg instruction used to find the two's complement of a number. We will learn about different number extensions, signed and unsigned. We will learn about the signed versions of the instructions multiply and divide. We will also see an example of combining number extension with arithmetic operation. Let's begin. The neg instruction. Neg means negate. The signature of this instruction, or the way it usually looks like, is like this. Neg followed by one argument. The neg instruction allows to change the sign of a number using the two's complement method. In fact, the neg instruction just does the following. It flips all the bits and finally adds 1 to the number, just like we have learned about the two's complement. For example, neg EAX changes the sign of EAX. For example, if EAX may be represented 3, then after invoking this instruction, neg EAX, EAX will contain the two's complement of 3. Of course, that because EAX is of size 32 bits, then neg EAX is going to invoke the two's complement in 32 bits. Another example is neg BL. In this example, we change the sign of BL. Note that because BL is of size 8 bits, the two's complement is going to assume lengths of 8 bits. Let's see an example. I'm going to show you an example of 8 bits just because it is convenient. However, neg works for any size of argument. It is going to work both for 8 bits, 16 bits, and 32 bits. It even works for 64 bits if you work in long mode. So let's look at an example. We put 3 inside AL, and now we use this instruction, neg AL. So initially, AL looks like this. This is how 3 is represented in base 2. Now we do the two's complement. I remind you that we have to do two different things. First, we have to flip all the bits, which means that we turn every 0 into 1 and vice versa. And then we add 1. First we flip every bit and then we add 1. And finally we get this number, FD, which is going to be the result. After using this instruction, neg AL, the value of AL is going to be FD in base 16. Some words about sign extension. Let's look at this question. We have a number of size 8 bits and we want to extend it to 16 bits. How can we deal with the sign? Maybe you don't fully remember it, but for example, in a number of size 8 bits represented in the two's complement, the sign bit is the highest bit. It is bit number 8, or maybe if you begin counting from 0 from the right, then actually it is bit number 7. But it doesn't really matter, it's the last bit. So how can we extend this number of size 8 bits, which is signed, to a number of 16 bits, which is signed, so that the value of the original number will move to the extended number? We also might want to extend from 16 bits to 32 bits or some other kinds of extension. We might want to extend 8 bits to 32 bits and so on. Let's look at an example. We know that 5 is represented as this number in binary. If you are not sure, let's check it out. 1 plus 4 equals 5. Minus 5 is this number. How can we know it? We just flip every bit and then we add 1. You can check that this is going to be the result, assuming 8 bits length. Now let's try the naive idea of adding leading zeros. If we want to extend this number to 16 bits, we are going to get this new number. There is some separation here, but please treat it as one number. I just separated so it would be easier to look at. And we get this number of size 16 bits in base 2, which is 251 decimal. It's not really what we wanted to get. We expected to have minus 5, because we began with minus 5 and we just extended it to a bigger container. We don't want to get 251. Let's try something a bit different. Maybe we try to add leading ones. Leading zeros didn't work. Maybe leading ones is going to work. And we get this in base 2, which is surprisingly minus 5 according to the 2's complement of 16 bits. So this time we got it right. Maybe we can get some conclusions from this example. It seems like extending positive numbers could be done using adding leading zeros. However, if we want to extend negative numbers, we should add leading ones. It could be cumbersome or maybe inefficient to do this yourself. Thus, there are two types of instructions that could help you when you want to do this kind of sign extensions. There are two different ways to do it. You can extend while moving, which actually means that you move one value from one container to another, and while doing it, you are also extending it. There is also another way, which is mostly about extending numbers inside EAX, or inside EAX and EDX together. And don't worry, we are going to take a look at each of those instructions and see examples of using it. Let's begin with move zero extension. It looks mostly like the move instruction. If you remember, also the move instruction has destination and source. However, move zero extension, in contrast to the move instruction, can actually get two different arguments of different sizes. It assumes that destination is of larger size than source. Why is that? Because we are going to extend source into destination. So destination is going to be at least as large as source. What move zero extension actually does is copy and then zero extend the source into destination. Move zero extension only knows to zero extend numbers. It doesn't one extend them, for example. Only zero extension. This kind of extension is unsigned extension. It does not care about the sign. For example, move zero extension, EAX, BL. This instruction extends BL using leading zeros and stores the result into EAX. This is actually equivalent to first zeroing EAX and then moving BL to the lowest part of EAX, which is AL. You might ask, why not do these two instructions? Well, it's better to use one instruction. Also, your intention is going to be much clearer when you use move zero extension. When you use this kind of instruction, it is clear that you want to extend the number and to store it inside a larger container. Another example, which is basically pretty much the same, this instruction extends from 8 bits to 32 bits, and this one extends from 16 bits to 32 bits. Again, it just adds leading zeros. Nothing very special about it. This instruction, move zero extension, should be used when working with unsigned numbers. Don't mix it up. Don't use it for signed numbers, because signed numbers do not extend very well with zeros, as we have just seen. I remind you that when we tried to extend -5 to a larger number, to a number of size 16 bits, if we try to do this with leading zeros, it doesn't work. We got a strange number. We got 251. But when we tried to do it using leading ones, it did work. Next, we look at move sign extension. It has the same signature as move zero extension. It has a destination and source, exactly 2 arguments, and we expect the destination to be larger than the source, to be larger by size. Just like move zero extension, move sign extension copies and sign extends source into destination. However, this time note that move sign extension sign extends the source into the destination. It's not just about adding leading zeros. Move sign extension is smarter. It can check the sign and then extend accordingly. It means that if the last bit, the highest bit, is 1, move SX is going to use 1 extension. However, if the highest bit is 0, then move sign extension is going to use 0 extension. It is more flexible than the move 0 extension instruction. Let's look at an example, which is basically like the example in the last slide. However, this time we use move sign extension. Let's look at this. Move sign extension EAX BL. This instruction extends BL according to BL's sign. If BL's highest bit is 0, then the instruction extends BL using leading zeros. If BL's highest bit is 1, then the instruction extends BL using leading ones. This instruction, move SX, actually understands signed numbers. Let's look at another example. Move SX, ESI, CX. This one extends 16 bits into 32 bits. I remind you that the previous example extended 8 bits into 32 bits. You can use any combination that you like as long as the destination, which is the left-hand argument, is of larger size than the source argument. So this one, not very surprisingly, just sign extends CX and then stores the result into ESI. The move SX instruction should be used when working with signed numbers. If you are using unsigned numbers, then you are going to get wrong results if you use move SX. So do the separation. Whenever you work with unsigned numbers, use move zero extension. Whenever you work with signed numbers, use move sign extension.